Hello, my name is Alexander Toler, and today I will be walking you through my research with size-exclusion chromatography. As humanity begins to explore the concept of space travel in a more practical sense, a key component to our success will be the quality of our building materials. And while metallic components such as steel, titanium, and aluminum-based compounds are largely important to the successful construction of spacecraft, they require a co-development of non-metallic compounds such as carbon-based polymers to succeed. And in advancing the development of these polymers, post-synthesis quality control is critical due to the harsh environment they will be forced to withstand. Our research seeks to improve one of the existing methods of quality control in gel permeation chromatography by examining factors that will affect the results of analyses run using this method. When it comes to the production of spacecraft, the inclusion of specialized polymers is extremely important as these polymers serve a wide array of functions that cannot necessarily be handled by metallic components, such as forming the basis of a craft's exterior heat shields, or even something as minute as serving as insulation for electrical components of the craft. However, due to the harsh environments encountered by spacecraft, it is crucial that these polymers be designed so that they may resist the effects of the environment while maintaining key properties such as polymer composition, polymer size, conductivity, and malleability. Post-synthesis, polymers are subject to a battery of tests in order to make sure that there are no anomalies or imperfections among the batch. Among these quality control methods, we will be focusing solely upon gel permeation chromatography. So what is gel permeation chromatography? Gel permeation chromatography, or GPC, is a subtype of size-exclusion chromatography, a type of chromatography in which analytes are separated by effective molecular size. In GPC, the column is packed with porous silica particles, which trap smaller analyte particles and allow larger ones to pass through relatively unhindered, effectively sorting them by size. The silica particles that are used as column packing in GPC come in two varieties, the fully porous particles and the superficially porous particles. Fully porous particles are porous all the way through the core of the particle, and it is possible for analytes to diffuse all the way through the particle or to diffuse in and out of the pores. For superficially porous particles, however, they consist of a solid core surrounded by a porous shell, which effectively allows for a shortened diffusion path as the depth of the pore is decreased. Superficially porous particles offer many advantages over the standard fully porous particles, such as reduced column back pressure, higher efficiency separations, a higher number of plates per unit pressure, and higher peak resolution. In this experiment, our objective was to obtain a deeper understanding of how separations of low-weight polystyrene standards utilizing columns packed with superficially porous particles would be affected by various broadening mechanisms. The broadening mechanisms that will be explored in this experiment are diffusion, mass transfer resistance, and sample polydispersity. However, at this phase of the experiment, we are focusing our efforts solely upon the effects of diffusion. Stop flow separations were carried out utilizing columns containing superficially porous particles with pore sizes of 90 and 160 angstroms, respectively, and a series of low-weight polystyrene standards ranging from 162 daltons to 6.2 megadaltons. The effects of diffusion were measured utilizing a stop flow setup similar to that pictured right. The mobile phase for this experiment was an organic solvent called tetrahydrofuran, or THF, and was set to a consistent flow rate of 0.5 milliliters per minute throughout the experiment. For each column, toluene was used as a reference sample due to its structural similarities to styrene, the monomer subunit that makes up polystyrene molecules. A sample of polystyrene would be injected into the sample loop and then injected into the system using a switch. THF would then carry the sample through the system until it reached the halfway point of the column, at which point flow would be shut off using a flow switch for a predetermined amount of time. During the period in which there was no mobile phase flow, diffusion was free to occur without interference from the flow-based broadening mechanisms such as mass transfer resistance or sample polydispersity. Upon completion of the predetermined stop flow period, mobile phase flow would be resumed utilizing the flow switch. The sample would then be carried from the column to the detector, where the signal would register and generate a chromatogram. The effect of diffusion on the peak shape would then be measured by observing the peak shapes generated in this chromatogram. Pictured to the upper right is a composite graph of the average absorbance values for the 4 stop flow periods performed for the 4.9 kilodalton polystyrene sample on the 90 angstrom column. The graph shows that as stop times increase, peak shapes tend to widen, as the 0-minute stop has the narrowest peak, while the 480-minute stop has the widest peak. Pictured to the bottom right is a linear plot of stop times of the 4.9 kilodalton polystyrene sample between the 90 angstrom column depicted in blue and the 160 angstrom column depicted in red. These lines can be used to calculate an effective diffusion coefficient for each column, and the higher slope of the 90 angstrom line can lead us to the conclusion that the 90 angstrom line will display a higher calculated coefficient. In the future, we intend to take this experiment in several different directions. Firstly, we plan to run experiments on a 1000 angstrom column in order to determine how columns featuring larger pore sizes are impacted by broadening mechanisms. Data from previous experiments will be compiled in an effort to create a column that mixes 90 and 160 angstrom pores in order to create a column that possibly overcomes the narrow weight range of the 90 angstrom column while reducing the proclivity to diffusion found in the 160 angstrom column. And lastly, in the near future, we intend to expand upon our research by studying the effects of diffusion in open tubes rather than confined columns.